Hello, welcome to the course Transducers for Instrumentation. Last lecture we discussed some optical detectors, mainly the photodiodes or PIN diode, and we saw that the structure of this photodetector is P-type, intrinsic and N-type. There are three regions, and the intrinsic region is has very high electric field because we bias this photodiode in always in reverse bias. So intrinsic region has very high electric field, and a photon comes in and it generates electron hole pair, and that electron hole pair gives rise to the electrical voltage or the current, which we sense across a load resistor as a electrical output. So this we saw, and then we discussed some of the equations which govern how many photons will be absorbed in a particular distance when we shine a light on a material, because not all the photons are absorbed on surface itself. They actually penetrate the material, they go well inside, and there is a kind of exponential relation of absorption with the distance. So this we discussed last lecture. Today we are going to discuss the avalanche photodiode, which is we call APD. Unlike PIN diode, where the electrical output is kind of say equal to, or the kind of corresponding to number of photons received by the device, because one photon give rise to one electron hole pair, and that gives rise to 1 unit of charge outside. Unlike PIN, in avalanche photodiode, if a one photon comes in, then we have a very high electric field in the intrinsic region, so that the generated electron hole pair, they acquire energy from this very high electric field, and they acquire so much of energy that this same electron can itself knock down one more electron hole pair. So this is kind of a chain reaction. One electron hole pair give rise to two electron hole pair, and these two electron hole pair give rise to four electron hole pair. So this is a chain reaction, and suddenly within fraction of seconds, we get so many electron hole pairs that a reasonable amount of current flows in the outside load. So a single photon give rise to significant current, so we have some sort of a gain in the avalanche photodiode. So we are going to discuss today avalanche photodiode. So this is avalanche photodiode, or we call it APD in short, and the structure and electric field profile of this APD is something like this. We have the similar region, for example, we have this N plus here, and then we have a P region here, and this is intrinsic region, and this side we have P plus region. And all these photodetectors are always biased in reverse bias mode. So we have a external voltage which is connected in reverse bias, means the positive terminal is connected to N plus and the negative terminal is connected to P plus through a load resistance across which we will measure the output voltage. So this is our R load. This is my electrical output. So this is the structure of APD, or avalanche photodiode, and we have intrinsic region which is connected to P type this side, and which is further connected to N plus. If we plot the electric field profile of the same structure, this looks something like this. So we have a very high electric field buildup during in this vicinity, where N plus and P are joined together, because this is a very heavily doped region, so the electric field will be very high in this. This is electric field. With respect to x, which is the distance across this device, and the electric field profile look something like this. We have a peak at this point, and then there is a constant field profile, because intrinsic region the potential will be dropped linearly, and then we have like this. So this is the electric field profile if we apply a certain voltage across this APD, and we see here there is a peaking of electric field happening at this interface N plus and P, and we call it avalanche region. And this is our depletion region. And the physics of working of this device is exactly same, where we have intrinsic region where photon will strike and it will knock down electron hole pair. Now this electron hole pair will move towards the terminal where this charge carrier see a avalanche region. Avalanche region is a short region where the electric field is very high, as we can see in this field profile. Because of this very high electric field, these charge carriers will start gaining energy when they are moving through this region. So they will acquire enough energy so that this electron or hole, they can knock down one more electron hole pair by releasing that energy to the lattice. This generated electron hole pair will further move according to the electric field and start gaining energy from electric field and knock down again one more electron hole pair. So this is a chain reaction. One photon gives rise to one EH pair or electron hole pair. This one EH pair gives rise to two EH pair, 2 gives 4 and 4 gives 18, and this is like a geometrical series. So we get at the end a very high current in the output load, which is the R load. So one single photon gives rise to a significant current in the output load. So we can say that there is a gain in the device where this gain is multiplied to the number of photon received. We get let's say 100 photons, but that 100 photon give rise to 1 million kind of electron hole pair. So this is a gain in terms of the signal. So this is the structure of APD. Now let's write down few important points. So the APD has an internal gain M, which is obtained by having an electric field in fact high electric field, that energizes photo generated electrons. The second point is these electrons ionize the other bound electrons in the valence band upon colliding with them which is known as impact ionization. Then these newly generated electrons and holes or are also accelerated by the high electric field and gain energy to cause further impact ionization. This phenomena is actually called the avalanche effect, and hence the name of this device is avalanche photodiode. This phenomena is called avalanche effect. So we see that this avalanche photodiode generates multiple electron hole pair even with a strike of a single photon, it means there is a gain which we can say m times. It depends on the device geometry and it depends on how much reverse bias we applied, how much is the electric field profile. So depends on all those things. This gain actually depends on those profiles. But this APD has an internal gain, and one photon gives rise to m number of electron hole pair, and accordingly the current which is proportional to the number of charge gap. So this is the avalanche photodiode, which is second type of photodiode which we use for these optical detection. Let's see some of the numerical problems what for the equations we just discussed last lecture. Let's have some of the examples based on that. So we have an example here. So we need to find out the maximum value of the energy band gap. Energy gap, or we call it band gap, which a semiconductor used as a photodetector can have if we want to make for yellow light, for example. And when we have yellow light, it means we know the lambda for yellow light, which is 600 nanometer. So this is the example. So let's see what is the solution. So here we want to make a photodetector which is sensitive to yellow light. It means it should detect when the yellow light is coming, and for the yellow light its universal uh, value that yellow light has a lambda of 600 nanometer. So when yellow light will come, the photons the yellow light carries, they have a certain energy which is equivalent to the 600 nanometer wavelength. So we need to find out that much energy, what is the energy of those photons, and if the energy of these photons are more than the band gap of the material, more than or equal to the band gap of the material, then the material can absorb these photons and generate equivalent amount of electrical signal. So we need to find out how much is the energy of this photon, and our band gap of the material should be equal to or lower than this the energy of these photons. So for the limiting case, we take band gap as equal to the energy of photons. So to calculate energy of photons, we know E, the energy of photon, is equal to hc upon lambda, where h is this Planck constant, c is the velocity of light, and lambda is the wavelength of light. So we can put the values here. H is 6.626 into 10 to power minus 34 multiply by C, which is 3 into 10 to power 8, and divide by lambda, which is 600 nanometer. So we need to convert it into meter. So 10 to power minus 9, and the value comes out as 3.3 into 10 to power minus 19 joule, or you can express it in electron volt, which is more relevant for the band gap calculation. It comes out 2.07 electron volt. So here we see that if we use a material which has a band gap of 2.07 electron volt, it means it can absorb the photon of yellow light and it can produce electrical signal. So this material which has band gap of 2.07 electron volt, it can act as a good photodetector for yellow light. So this is how we calculate the band gap of material, which material should be used for which kind of light. Let's take the second example. Say this is one. So a photodetector whose area is given, let's say 5 into 10 to power minus 2 centimeters per centimeter square, is irradiated with yellow light whose intensity is 2 milliwatt per centimeter square. So now we assume that each photon generates one electron hole pair in short we can write electron hole pair as EHP. Then we need to calculate the number of electron hole pairs generated. Generated per second. So here is example. We have a photodetector whose area is given 5 into 10 to power minus 2 centimeter square, and we irradiated this area using yellow light, for which we already know the energy of the photon, and the intensity of this light is 2 milliwatt per centimeter square. So when we shine this area with this much of intensity of yellow light, how many electron hole pairs are being generated? per second. So this is what we need to find out. So here the assumption is that each photon generated gives rise to one electron hole pair. It means the efficiency or the quantum efficiency of these photons are 100%. All the photon give rise to a electron hole pair. So here the assumption is efficiency or the quantum efficiency is 100%. So this is the assumption we are making. Then we can calculate the number of electron hole pair generated per second is equal to the number of incident photon per second. So the number of incident photons per second is equal to I, the photocurrent, divided by the charge of electron, which is equal to the P naught, the incident power of photons, divided by h nu or hc by lambda, which is the energy of a single photon. So these two quantities are equal because we are assuming that the quantum efficiency is 100%. Now we can put these values together, where I ph over E is number of electrons per second. So we can calculate from this equation that P naught upon h nu is equal to 2 into 10 to power minus 3 multiplied by 5 into 10 to power minus 2 in watt, divided by h into nu, which we have calculated in the earlier example, this value, which is 3.3 into 10 to power minus 19, and the value comes in 3.02 into 10 to power 14 per second. So in this example we see, if we irradiate this photodetector with intensity of 2 milliwatt per centimeter square with yellow light, then how many number of electron hole pairs will be generated, assuming that each photon is giving rise to electron hole pair. So 3 into 10 to power 14 electron hole pairs will be generated in the material or in the photodetector, and this will come out as an electrical signal across the load resistance. So these are some of the examples which we can try based on the equations we discussed for photodiodes. So we discussed two photodetectors. One is PIN photodiode and the Avalanche photodiode. Next we are going to discuss the source, the optical source, which can generate the optical signal or the optical photons from the electrical signal. We apply electrical signal on the device and it generates the optical photons, which we can couple to the optical fiber, and optical fiber carries these photons to the long distance. So let's discuss the photo source. photo source or optical source is nothing but a light emitting diode. So we have LED, we call it in short. So this is a diode which is forward biased and it gives rise to the optical photons, and we call it the light emitting diode, and the structure is also very similar to a normal LED. So we discussed LED, the light emitting diode. A light emitting diode or we call LED in short is a device which converts electrical energy to light energy or to optical energy. And these devices are quite inexpensive, robust, and have long life. These devices can be easily modulated. It means switch on and off at high speeds. The third is this can couple enough output power over a small area to couple to fibers. So we have these LED or the light emitting diodes, which is a device which converts electrical energy into the optical photons, the optical energy. And these LEDs has certain properties. First is these are very inexpensive. In nowadays, with the progress of microelectronics, these LED devices are very inexpensive. These are quite robust because these are solid state devices, so uh, they are quite robust in harsh environment as well, and have a very long life because there is no moving part. They can be easily modulated because the size of these LEDs are very small and junction capacitance is also very less. So we can modulate or we can turn them on and off at very high speeds, which is desirable to send these optical signals. And we can couple enough output power from these LEDs because the area where the light is being emitted, that region is very small, so we can easily couple that to optical fiber efficiently, so that all the photons which are generated by LED, they couple to the fiber and they go inside the fiber. So these are some characteristic of LED as a optical source. Then we have two types of phenomena. One is called photoluminescence and one is the electroluminescence. So these are two different phenomena occur to generate these photons. Let's discuss them as well. So the first one is the photoluminescence. In this, the electron hole pairs, these excess electron hole pairs, are created by photon absorption. The photon is emitted by recombination. This process is called photoluminescence. And the other phenomena is electroluminescence. Where this excitation of these excess carriers is a result of an electric current caused by an applied electric field. And this happens, for example, in LEDs. So we see here two phenomena. One is photoluminescence. In photoluminescence, a electron hole pair combines and they get annihilated, give and releasing the amount of energy. This energy is released in terms of a photon. So photon get generated by annihilation of electron hole pair. So this is photoluminescence. In electroluminescence, a current is passing in the device and this current gives rise to the the energy is actually released by the from this current, because the current is the flow of electrons. these electrons acquire energy from the applied electric field, and this extra energy is released in terms of photon. So the photon generated in this process is called electroluminescence. So these are the two phenomena, and electroluminescence actually happens in LEDs, or the light emitting diode. So let's see how this happens in terms of the energy band diagram. When a junction is made of p-type and n-type material, the Fermi levels on both the sides are not aligned. Because the Fermi level for a system in equilibrium should be uniform the band bending takes place. So now we have two material, one is p-type and one is n-type, and remember this material is not silicon material, this is a direct band gap material, because as we discussed last lecture, for optical photon generation we need a direct band gap material. So this is a direct band gap material, for example gallium arsenide or so. So now we have p-type material and n-type material. When we join them together in equilibrium, the Fermi level should be uniform. So but for individual material the Fermi level is not aligned. So when we join them together, the band bending takes place, and we can draw the band diagram for this structure. We have this first side where we have band something like this, and on the other side we have like this. So let's say this is p-type, where this Fermi level is close to the valence band. So this is our EB and this is EC, the conduction band energy, and this is our Fermi level, and our intrinsic Fermi level lies somewhere in the middle. This is our EI, the intrinsic Fermi level. Now when we join them together, these Fermi levels actually in equilibrium, this Fermi level should be flat. So the band bending takes place, which looks something like this, and here like this. So we have the band bending, and this region is formed as a intrinsic region which is depleted of charge carriers, and sometimes we call it the depletion region as well, because this region is depleted of charge carriers. And in this we have certain holes which are in majority in p type, and we have some electrons, let's say this one, they are in majority in n type region. And the energy band gap is, let's say, Eg, which is uniform in both the sides. Eg is the band gap between this level and this level. This is Ec, this is Ev. Okay, so now we have drawn the energy band diagram of LED in equilibrium, where we are not applying any bias to this device. When we are not applying any bias, it means the Fermi energy, the Fermi level remains flat, and because in the p side, Fermi level is close to the valence band, and in the n type, Fermi level is close to the conduction band. If these level need to be aligned, it means the band bending will take place, that's as shown here. And when we join them together, there is a depletion region formed. This region is kind of depleted of mobile carriers, just like our normal diode. This is what happens in our diode. The depletion region forms. The same thing happening here, the depletion region is formed, and the band bending, whole of the band bending is taking place in the depletion region. When the band bending is taking place, it means we have a certain electric field available in this region. So depletion region is the region where all the electric, whatever voltage is applied, that whole voltage will appear across the depletion region where the band bending is taking place. If there is no, if there are, the bands are flat, it means there is no potential applied in that particular region. So when we apply a voltage bias across this device, this band bending will be further high, and that causes a high electric field. This electric field gives the energy to the moving charge carriers. So this is what happens when we apply the electric field. So the LED works in the forward biased case. The carriers diffuse to the other side of the junction, where they can combine quickly so we can draw the Same energy band diagram in when we apply a voltage. This is EC, this is EV, the valence band, and now we apply a voltage across this device. This is a forward biased voltage. So when we apply a forward biased voltage, these electrons will start moving towards p type, and these holes which are on the p side, they will start moving towards an n type. This is the intrinsic region. Or the depletion region. So now we have this device and we apply a forward biased across this device. Now electron and hole will see a field which is pushing them towards the other side. Now when this electron from n side, where this is in the axis or the majority carrier, when it moves to the p side where this is a minority carrier, and it can recombine there because there are so many holes available. So when this electron and holes will recombine, they will release the extra amount of energy in terms of a photon, and this photon will come out as a optical photon, and this works as a LED or the light emitting diode. So this device, now these electrons can recombine and give rise to a photon, all these recombination will give rise to a photon. So this is how this LED works. The recombination of electrons and holes also takes place non-radiatively, which reduce the output of the device. So we see here that these electron and holes are recombining and emitting the extra amount of energy as a photon, but sometime this release of the energy is non-radiatively. It means this does not lead to a photon, but it is given as a kind of phonon to the lattice, and the device actually heats up instead of emitting a photon. So This phenomena actually reduces the output of LEDs, hence there is no 100% output, and some of the energy is actually wasted in terms of heat in the device. So let's consider some equations for all these devices. The fraction of electrons that are injected into the depletion layer which results in photons getting produced is called the internal quantum efficiency. Or eta of LED. So if n is the number of electrons injected, into the depletion layer, every second, the power output of device is given by P is equal to eta, which is the internal quantum efficiency, multiply by the number of electron injected into the depletion layer, and multiply by the energy of a single photon, which is h nu. So this is the power output of this device, or we can also write it some like eta I into h nu upon E. E is the electronic charge. Now if the energy of photon is measured in electron volt, the current in milliamp the above expression becomes P, the power in milliwatt, is equal to eta E gamma into I. So these are the formulas to calculate the output power of a device when the number of electrons which are going into the depletion layer is known, eta is known, the quantum internal quantum efficiency, and the energy of a single photon is known. So let's have one example based on this. A gallium arsenide LED radiates at 900 nanometer. If the forward current in LED is 20 milliamp, calculate the power output assuming a quantum efficiency of 2%. So in this example, it's given that we have a gallium arsenide based LED, and this LED radiates at 900 nanometer. So 900 nanometer is the wavelength of photon. It means we can calculate the energy of a single photon, how much is the energy of a single photon it radiates. If the forward current in LED is 20 milliamp, it means 20 milliamp current is flowing. By this flow, we can calculate how many electrons are actually injected into depletion layer per unit time, per unit per second. So if the current is given 20 milliamp, we know number of electrons going there, and the quantum internal quantum efficiency is given as 2%, which is a reasonable number for this internal quantum efficiencies. It's in the range of this only. So now let's find out the power of this device. The energy of the photon first we calculate. In electron volt is Hc upon E into lambda. This we can put down the numbers for Planck's constant, which is 6.62 into 10 to power 34 into 3 into 10 to power 8 divided by 1.6 into 10 to power minus 19 multiply by 9 into 10 to power minus 7, which is the wavelength of this photon. This number comes out to be around 1.38 electron volt. So this is the energy of a single photon. Now we can calculate the power output. P is equal to 0.02, which is the efficiency, internal quantum efficiency, multiply by the energy of a single photon, which is 1.38, multiply by the current, which is 20 milliamp here. So the power output of the device comes out to be 0.55 milliwatt. So this is the power of this gallium arsenide LED. So this is how we calculate the power of any LED, which is in terms of for energy of single photon and how much current it is flowing. So today we saw one optical detector, which is Avalanche photodiode. Then we discussed optical source, which is LED, and we saw the band diagram how a LED generates the photons, and these are some examples to calculate how many photons or how much the power of this LED is. So this is all for today. Thank you.